All right, cool. So now we are live, and today's workshop, the Data Science Club, is on understanding dynamics using statistical models. And yeah, so I am a fifth year in systems biology at Columbia, and I mostly analyze observational data, whether it's from the FDA or electronic health records, to understand different aspects of biology and medicine. I often integrate that with public biomedical databases. Don't do as much with genomics data directly, but I do that as well when needed and collaborating. But today I'm gonna kind of go over different modeling techniques when in looking at observational data, and I'll show how that looks like. So I will share my screen. Um, and so yeah, so for today's workshop, I made a repository on GitHub called Cam Workshop. It's found at this link, and I made a library for this workshop. So it's easy to make an R library. It's well documented. There's a whole book on it, and it's not hard to get through it. I read it a couple hours over the holiday break, and so it's kudos to the art studio team for and others for putting that together and doing all the hard work. So, but yeah, so the goal of today's workshop is to present some modeling strategies to understand drug responses across childhood using large observational data. And so that's what I do a lot in my thesis work, and I kind of want to share kind of some of those investigations today. So I'm in a library called Cam Workshop, and really just houses data. So our packages can provide just code, both code with some data, or they can be primarily for storing data. Um, and that's what I'm using it for. And then the other cool thing, another package called Pacman. It's very good for loading and installing libraries very simply. So I'm using that. So actually, payload here is a combination of installing libraries if they're not installed on your system, and also then loading them. So I have a bunch of these libraries that I'm using today. I'm not specified. I'm not gonna open this in our studio and kind of go live coding. But if you want to, you can just clone the repo by copying the link and do a git clone. No cooler than opening the notebook readme. And then some other settings. Another cool thing in notebooks, you can set a theme for how your plots look. So we're gonna set that up top, make them larger, make them bold, make the text bold and the figures make it nice looking. So I guess starting with the punchline, generalized additive models I found show improved nonlinear associations both in interpretation and fit compared to linear models. Well, compared to, well, they are a linear model, but compared to simple linear models. And I'll go more into detail what generalized additive models are. But they're just a easy way, an easy implementation wise, to incorporate nonlinear associations to a response that you're interested in. And so, usually what we do all the time is we try to characterize or to understand the relationship between a characteristic and an outcome. And often that relationship we think is, we say is linear. So like when you read papers, often you see the odds ratios and confidence intervals. And I look at a lot of stuff in randomized clinical trials that we see a lot of these days during the pandemic. These are from linear models, and it assumes that the relationship to the outcome is linear, that a change in the characteristic results in a corresponding change in the response. So modeling techniques are a good way to understand these relationships. So that's why I'm gonna go over them more. In my work, I want to evaluate relationships between drug exposure and adverse events. Um, Ultimately, trying to say that exposure to a drug may lead to an adverse effect or is related to an adverse effect happening. And I actually want to do this in children. That's kind of my focus. But I want to do this in a way that it's the relationship I'm trying to understand is not biased. Meaning that I don't want to just say there's a linear relationship, that the one small change in the characteristic results in a change in the response. The same way throughout the whole range of the characteristic. So I want really to let the data tell me what the relationship may be. So I'm interested in how side effects are related to a drug exposure across childhood, and so in childhood is a very heterogeneous spectrum. It's also very dynamic in time. I want to understand how the occurrence of a side effect may change across child development stages. So a lot of people think in childhood about it in stages, and I'm not going to break from that mold at first. So I'm just going to look at stages for now. So in this tutorial, I'll show how linear models and also generalized additive models are flexible yet interpretable ways to model relationships in a population, and GAMs have advantages over traditionally used methods. So the question primarily I'm asking is, and you want to start with a well-defined question whenever you do some kind of modeling or trying to understand a relationship. This way you can better specify the model you're using. So I'm asking which population model shows a quantitatively improved association between an adverse event with a drug exposure as it is reported at and across child developmental stages. So at the end, I'm kind of compare the simple linear models and also the generalized additive model and show quantitatively how they compare. So for the data, I made this R package. It stores the FDA's reports collected from clinical trials, lawyers, doctors, pharma companies, etc. For this, on the occurrence of methylphenidate exposure, which is a stimulant often used in treating ADHD and other learning disorders and other things with paranoia adverse events. And these are kind of termed by standard vocabularies. So this is a known adverse drug effect. I have references. They do work, so you can check them out. Of this association, and the mechanism has been thought as inhibiting dopamine neurons. You can look at that reference. And it has long-term side effects such as a change in brain chemistry and signaling. So if you take it for too long, and I'm pretty sure we take it for a long time during adolescence, it's not a great thing. But I have over 300,000 reports of all drugs and side effects reported for over 3 decades for the FDA, and this is all public. It's on their server. You have to ask them for an API key to get their data, and then you have to like pre-process it and all that. But I did it all for you guys, so it all looks really nice. So in the report.
Sorry, I have a quick question.
Yeah.
So here you're relying on the diagnosis of paranoia, right? And I'm assuming there's like there's no actual biological verification that their dopamine is inhibited or whatever. It's just a doctor saying they're paranoid.
Right. Yeah. So this is gonna be like a course example. And I'm not trying to like make it very molecularly connected. I wish I did, but and also yeah, probably the adverse event is not totally well defined here, but there are different ways to get other adverse events that are related to paranoia using standardized vocabulary. So you can think of these vocabs as being like a hierarchy or being like a Christmas tree, and you can start from the top and then get everything at the bottom. All the different terms of adverse events. And also like when you would actually want to do these studies, you want to like collaborate with, like what I do is collaborate with pediatricians or other doctors to really make sure that the adverse events you're looking at are meaningful. Like you said, like making sure that there's the mechanism like there. Yeah.
Yeah, that was kind of I guess the better question. Thanks.
Yeah. But that's really right. Yeah. So I would have to, whenever I would do this, I would just kind of like talk to a physician and make sure that what I'm looking for is if it's clinically plausible. Yeah, exactly. But for today, the purpose of today, I just chose these two different things that have been reported together, and so that's what I chose to look at. So the data from the package can be loaded by the data function report that. I just do some simple like convert what's gonna be loaded as integers and make it a factor. And well, no, this is a character. This is the column, but I order it on this factor, and then I order on the data frame by age. And then I also factorize the child development stage. And I label it as NICHD because the NICHD at the NIH they use these child stages in their primarily in their clinical trial regulations. And that's how they define the different stages, and so I use what they published on. And in the modeling, you can model with the methods here with characters. So I convert them to integer as well. So we have NICHD and NICHD underscore int. But anyway, the full data frame has over 300,000 reports. And it looks like this. So you have a bunch of report IDs, the age in year units. So this is very young. And then I rounded the age to years just to have it using. And then I have the stage and the indication of the drug area event. And so first when people look at relationships between drug exposure and adverse events, they often look at just a co-occurrence. And so that's what I do here, and I use ggplot, which I still think is the best way to visualize data. And so you can see that. So I have the other events with other drugs, or other events with the drug, or the event with the drug and the the bottom right is what we really are interested in. So we don't have a lot here that's publicly available. So it shows there's no reports at the top there if it's your terminal stage, and that's probably due to, like this paranoia as it is as a term reported at those ages. Probably not. We can't really assess that. So the actual adverse events you would have to assess better to make it more general. But in any case, this is the data we're using today. And when we try to model things later on, we want to take into account the occurrence of the drug or the event, adverse event together, but also the occurrence of the event with the other drugs and the occurrence of the and the occurrence of the drug with other events. So we wanna, and that is what is often looked at in pharmacovigilance, which is the field of study that I'm in, and it's quantified. And associations are often quantified as the event prevalence ratio between the drug that was reported and when it was not. And so you can see I'm just taking ratios here, and I'm showing that the overall. So the PRR is called the proportional reporting ratio, and it is the ratio of the event prevalence with the drug and without the drug. And on top, I show the prevalence. NPR value is 2.8, so that's showing that. And there's a higher event prevalence with the drug than without the drug, about almost 3 times more. And then I show the PR within these different strata. So we cut the data up by stages and you compute the statistic in those stages. You can see that in early childhood was one of the highest event prevalence with the drug compared to not. Does this make sense to everyone? Kind of how I know I'm like going through these things fast, but the general idea is this is a common way stratifying the data on doing these event prevalence ratios to understand co-occurrence. All right, cool. So we see that the PRR says that there is an overall association between reporting of methylphenidate and paranoia, and this is not surprising by what's been published on. But we see this value is different at the child development stages, suggesting a dependent relationship on when the drug is taken / reported. However, this is still limited by the observations here, the reports, like Jocelyn mentioned, and there's other factors that can that compound and bias the associations you want to compute with the observations as is, like relative to the marketing of the methylphenidate, relative to who reported it, and the type of adverse event, and the formulation of the drug, and all those kinds of things that you want to take into account at some point in your analyses. But the main thing with using this statistic itself is that when there's no observations of the drug and the event together, reported together, the PR cannot be calculated at all. So like Jocelyn was mentioning, There might be some quality issues with the actual drug prescription and the event reporting. And so they're not reported together, there there's some fuzziness there, and there still might be a risk of an adverse event. That's paranoia, maybe not called paranoia, with the drug, methamphetamine or something like methamphetamine there. But if there's no observations, you have nothing to compute, and you would hope that not, especially at the stages like we have terminal natal infancy and toddler. I'm sure there would be a risk if a child at these stages did take methamphetamine. It'd be really bad, probably. But you can't compute anything because there's no raw reports. We could suppose that even though we do observe a direct association, there's still a non-trivial risk of the side effect if a child were to take methamphetamine, suggesting there is an added value in sharing information across child development stages. And this is where modeling strategies come into play to kind of make up room here. So now with modeling, these techniques allow for using all available data to fit a model or a hypothesis of the relationship between a characteristic and an outcome. So everyone knows the logistic regression is like the buddy next door, extremely popular approach for this type of binary association. Basically, it's an equation of a line. You have y equals mx plus b, and that's what logistic regression is. But we basically do some other things too. That we transform the y. I'm not going to show how that's done. But it can be found online and different books, and I can report you to those later. The equation's not looking too good right now on here, but imagine LaTeX does some magic and the betas look nice. It looks nicer in the actual. Do I have HTML in there? No, I don't, unfortunately. But if you were to knit the notebook, the equations come out looking good. So you would be computing why would be the log odds of the probable association with paranoia versus not paranoia. And the betas are called the coefficient values for the association with the characteristic, and the beta naught, that you also see in the equation, is the intercept term of the probability of the population reports that contain paranoia versus not paranoia. When methamphetamine is not reported. The characteristics we want to understand, the risk of is the child development stages with methamphetamine reported. So the mono specification should be an interaction between the two, because we want to understand the risk of drug exposure at a certain stage. Below, I'm going to show the coefficients for different models, and also what's called the AIC of the model, or the KK's information criterion. And that's a way to kind of quantitatively assess how well the data is fit by the model, given how it was specified. So the more characteristics or more beta values we have in the model will fit the data better. But too many characteristics make the model very complicated, and so the AIC is the quantified form of that trade-off, basically. And so what I did was, I'm going to do this for different scenarios. I made a function in R. The logistic regression model is done by the GLM function. And what I do is I give it the formula, like I can give the event paranoia from the drug report or methafinity, and -1 means without the intercept, so without the comparison on the event happening without the drug. And then there's other details here. I'm not going to go over them, but if you're really interested, let me know and I'll explain. But it basically is producing a data frame with the AIC and the quantify how the model fits the data, as well as with the beta coefficients and the formula that I use in the model to make the association. So I bind all the rows of the data frames from this function, GLM coef, and I put it into one big data frame, and I make the size for certain characteristics, for certain coefficients, the ones that represent the interactions that we care about. And then I plot those coefficients across the models. The different models are the different formulas. And it's not a very pretty graph, but it just shows that like the model on the left has two coefficients with the drug and the intercept, and then when you add the drug reporting with the stages of development, you have not just two, but you have 7 more about these other dots here, representing the risk of that event happening at the individual stages. And then the next one is the interaction, which is what we really care about. And it made those coefficients look bigger. And then you have on the right, you have the relationship with the stages themselves without the intercept. And the actual coefficient values don't really matter here. They're all not that great. There's some that are negative, which is not really informative. But the interaction model shows that there's coefficients with positive values that says something more about that there is a relationship between that there is a relationship between the concurrence of the drug reporting at a child stage with the adverse event. And then down here I'm showing so we want what I showed above was the co-occurrence statistic, the PRR. Now we would like that statistic to be somewhat related to the modeling statistics. And so I'm showing that relationship here and just plotting them against each other. And kind of see that there's really no relationship. And that's like you would hope that there was some linear relationship, but there isn't, and probably because the model is pretty biased in that it's assuming a binary relationship that's probably not doing a great job. And now I'm showing the AIC between the models. The higher the AIC, the worse the model fits the data. The lower the AIC is, the better the model fits the data. And there's really no like absolute number that is better. And what matters is really is the comparison between model AICs. And the point is that the model that includes the characteristics of the event reporting and the child development stages are better. than the models with just the individual characteristics. Though the model that doesn't have the interaction seems to be a little better with a lower ASC value. It doesn't really matter that much because the difference in AIC is pretty small, and also the model itself is pretty biased. And you can see that in the coefficient values. Like the intercept term, it's pretty negative, and you have two pretty negative values for different development stages. And you kind of want models that, the whatever characteristic you're looking at has some kind of sensical relationship. And we like it to we would like these coefficients to be somewhat related, but in the model they're not, and that's kind of at least for me, it's a problem. All right, I'll go to the next thing. Polynomial regression. Before I go into this section, anyone have any questions about logistic regression or what I showed so far? No? Cool. Alright, so polynomial regression is the next step to allow fitting nonlinear associations of characteristics. And so you think of the Pythagorean theorem. The Pythagorean theorem, you have like a squared plus b squared equals c squared. And those squared, you would say those are called degrees. And so the higher the exponent, the higher the degree in your equation, and that's what polynomial regression equations are, and they have higher different values of degrees. So like in this equation, beta x, this is a polynomial equation. The degree here is 1. And then in other polynomial regression equations, I think the degree can be 2, 3, 4, and so on. So here, I'm going to iteratively add more degrees of freedom, meaning, and in terms of the degree I showed with like the x squared, x cubed, and so on, those allow more places to break a line. So like y equals that. Y equals x is a linear line. Y equals x squared is like a parabola. Y equals x cubed is another shape. And that those can be thought of as where the line breaks and you have more breaking points. So that's what we're doing. We're gonna iteratively make more breaking points in our line to make an association to hopefully improve the association with the binary event. So again, I made a function. I took a lot of the equation, a lot of the function from a course online, but I kind of modified it a little bit. But I'll show pretty much. This is what the equation looks like. So, you have the event y, and then this is like the beta coefficient, and then you have the stage in the integer. So like 1 for neonatal, 2 for infancy, and so on. And the degree is 1. The AC here is 10,000. That doesn't make sense by itself, so don't pay attention to that. But the resulting probability of the event from this equation looks like a straight line, pretty much. There's some breaks because and then the equation makes some breaks here. And then you can add another degree equals 2, and then you can plot it, and it looks like this. So now you have a little kink at the right. And then you know degree equals 3, and you have more kinks, and then you add another degree, and so your equation gets huge. And you have other like betas here. And your equation looks like this. The line produced like this. And then the grade goes 5. And you can see too on the y-axis that's pretty small what the probability is, and that doesn't really make sense. So this already tells me that this is not a great model and probability specifications. Not very good. But yeah, so you can do that degree 6, and you get a line like this, and this sort of makes sense. And that early childhood is this is early childhood for middle childhood, early adolescence, and late adolescence. And this is where the PRR was calculated, and there were the most reports. And this is where the coefficients are the highest. And so this is somewhat of a good thing. But still, the equation doesn't make sense. And neither does the y-axis. And also the AIC values are not better from the logistic regression, though they don't make that much sense. The coefficients are low, and that's hard to interpret. Also, we can't intuitively add the drug reporting interaction into this model because of the need to multiply this factor into every coefficient degree, which doesn't make that much sense. It's like multiplying the drug reporting indicator by each of these, and that would be kind of weird, you know. No, that's not great. Now I'm gonna get into regression splines. These are cool, but before I do, anyone have any questions on polynomial regressions I showed? Alright, cool. Yeah, so regression splines are not too often used in this area of study, but they seem promising. They contain inherent model flexibility and the associations. And the idea is to stitch together individual bases or components of the association function. Now, what I mean is that, and I took this from a textbook, Intro to GAMS. It's a great book. I recommend it highly. But anyway, without going to the code, you see you can have 7 different bases, one for each child stage. And you see that each one is tailored to the certain stage. And then in the spline, you would sort of add them together. So now you're fitting a model, a spline model, that takes into account values at all the stages at the same time. Now, these components can have different shapes. Below I'm going to show what they look like. And one uses what's called a cubic spline. And that's related to the cubic shape. These have like a tent shape. And now I'm going to show one with a cubic shape. And those are like smoother. They look nicer. And I, again, took a lot of my stuff from Stack Exchange. And below you see that you can develop a function that individually stitches together different components representative of the data at the different stages. And that's done all together. And that's something that I more want. And so yeah, the business functions are calculated at what are called knots. And the knots are at by different stages. 1 through 7. And those are the different points in the data range. So you may have a data range from, I don't know, 0 to 100, and you can choose where your knots should be. And there could be 10 knots, 25, and they could be at different positions. Or, and what I'll cover below, the model can choose them for you based on your higher quality data. If you don't know what or where the knots should be, it's usually always better to let the data tell you. Well, here the shapes look kind of funky, but that's okay because I'm just showing that I want to have different representations of the data within my data range and do that at the same time. And I'm going to do that with generalized additive models. And these are great. These are really cool. I'm still learning a lot about them, but this is that they are really promising. And these are linear models, like logistic regression, but they can also contain nonlinear functions of characteristics. GAMs are most often used in ecological studies to study associations among time and space, or like in geography. But here I'm going to use GAMs to understand a drug response over time, or over childhood. And I'm going to show a couple of different ways we can specify GAMs and how we can understand the results from them. Now, again, I make a model function, and that I make a function that takes a GAM model and I extract different components of the model, including the coefficient and the AIC. Now I individually show what these can look like. So without going over everything, what the shape looks like is that. So on the x-axis you have different stages, and on the y you would have the probability of the event risk. And you see that there still is negative numbers, but you see that there's an increasing risk over time, and that's related to the PRR statistics we saw earlier, and that's a good thing for now. And then another model you can do is you can make a regression spline with an interaction with the bi-variable in this XS function. And another notational thing, the BS takes into account the type of shape you want the bases to have. And here I'm choosing penalized cubic spline. And what I mean by penalized is that there's a trade-off between how wiggly I want my line to be and how straight I want my line to be. And let the model itself determine that wiggliness. And that's what the BS specifies here. The general shape I want. And with the direction I can, I'm actually able to compute the risk at the stages without the drug, with other drugs, and then with the drug. And you can see that there's more of a hump at early childhood than over here on the left. And that's a good relationship with the higher PR we saw here. So that's a good thing, a good indicator. And the Y value means, well, no, the Y is not probability, it's the odds. No, there's two, a ratio to avoid higher odds of paranoia with the drug here. And then the other nice thing is, these lines are fed together. They're fit in the same model. So you don't have to do separate steps. And you always want to do things in like less steps if you can. And then now I do the same thing, but now I'm using an integer for the drug reporting, and that is not as informative here. Meaning that it's good to include the other drug relationship as well. And then you also do a different interaction. So before I used a spline, now I'm using a tensor effect. This doesn't assume that there's a relationship between the stages and the event. Or no, this doesn't assume that there's a dependence among the stages. But the model computes pretty much the same line. And then do this like before as well. That doesn't look as good. I'm saying that it's good to include modeling of the event with other drugs too. And now we can look at the actual coefficient values. Those are on the y-axis, and the values are on the x. And you can see that at least for the models that interact with both the drug and other drugs, and that the coefficients at the later stages are a little bit higher than the interaction with other drugs. And that comparison makes sense. And that's what we want our models to ultimately do. And then last thing, I look at the AIC in the model. And again, I see that the interaction models have a lower AIC, and actually, because they're below 10,000, those are lower than the linear models that were above. And that's a good thing. That means that the data is better fed by the model. Not by a whole lot, but there is some better fitting. Another yeah, this just shows that it's better to include the interaction of the stages with the drug and the stages without the drug in the same model. And that's because we can make comparisons of the coefficients together, and this sort of makes sense based on what we saw with the PRR statistics, that there's a higher event prevalence with the drug reporting than without. And you can't get that from the model without the comparison. And so that was really fast. Gonna look at regression modeling of nonlinear associations using observational data. It's not the best way to understand associations, but at least we show, I hope I showed that when you use a model that's more flexible, that produces statistics that make more sense, then that's the better option to use. Now, the interpretation of your results to have real world impact, there's a lot of caveats, like Jocelyn mentioned, about data quality and confounding, model bias and variance, and other utilization of results. And that's usually taken into account in analysis. But the thing is, you can include other characteristics like when the report was submitted and by who, and also like what other types of drugs were submitted with the report. And if you were to include that in your model, and that may reduce some of the variance that you would see. And that, in my opinion, was a better model. But in any case, what I showed today, GAMs show much promise in addressing these challenges. and most importantly, being able to answer the question that's being posed in a more precise way. So with that, that's the end of my quick intro. Anyone have any questions or want to talk more about what I mentioned? Thanks for giving me a good time to breathe. Yeah, so I hope you learned something today, and I know not everything is probably correct or well specified here. But this just shows your different options you have when you model things and want to extract relationships from data. And there's a lot of great tools to use. And a lot of great ways to look at data, model data, and extract insights. And hopefully you get something out of it to help you with your own work or problems.
Thanks, Nick. That was a really great talk, really great introduction to some types of modeling, and looks like a lot of good code that you put together and explanations that people can refer to. It's really good. And thanks everyone for coming as well.
Yeah, thanks, now. And
Thank you.
yeah, and feel free to post issues on the GitHub repo. There's an issues tab, and if you have any questions on some of the stuff, feel free to drop a line. Very cool. That concludes today, and hope to see you at a future workshop.
All right, and don't forget we upload all these to the YouTube as well.
Yeah, so I will be uploading that tonight.
Thanks everyone.
And, bye, y'all. Thanks.